Or we said that a function was well typed as long as the body was well typed, assuming the argument. Now that we've added let type to the language, we have one more premise to check. We need to know that that function argument type tau1 is valid in the current environment. In our implementation, that means we need to add one more line to the case for funny. Before we go to type check the function body, do a tvar check, and then proceed as before. Here's the rule that we'd like to implement for let type. A let type with the name D and the variants x1 and x2, and then the body expression E. This all has type tau0, provided that E has type tau0 in a certain environment gamma prime, and provided that those argument types tau2 and tau1 are valid in the extended environment. What's this environment? Well, it's our input environment extended with everything we need to know about the let type. There are three things in the extension. First, that D is a new defined type with an x1 variant and an x2 variant. Second, that x1 is a constructor function that takes in a tau1 and returns a D. Third, x2 is also a constructor function. This one takes in a tau2 and it also returns a D. And with that, we're in pretty good shape. Typing rule for match unpacks and uses this information from the environment. If we're matching on expression E0 with type D, first thing we need to know is that the environment contains a declaration for D. Then we check that E0 has type D. And third, we check the two branches. First branch with expression E1 gets checked inside an environment where that variable x3 is bound to the input type for that constructor. And then the second branch, E2, that's checked with x4 bound to the tau2 type. So that's the input type for the x2 variant. There are a lot of x's here, but x2 and x1, those are the tag names. x3 and x4, those are the arguments. Finally, we conclude that the whole match expression has type tau0, and that's got to be the same type that both branches have. E2 needs type tau0, and E1 also needs type tau0. One warning here, there's a subtle problem with this let type rule. We will get back to that later. For now, let's dive into the code. To type check a let type, the first thing we do is construct that extended environment. We add a tdef to the environment, and this has all the information that we need from the new type that we've defined. Next up, we use tvar check to make sure that the two types for our variant arguments are valid types. These types can refer to the type that we've just defined. They can be recursive and refer back to type name, but they can't refer to other types that have not yet been defined. That's what tvar check will look for. Finally, we type check the body, and we do that in an environment that's been extended even further to have types for those constructors. Our constructor type is just an arrow type. We'll reuse that, and that makes the type checker a little bit simpler. For example, if we have a let type for fruit, the first thing that we do is extend the environment with info about fruit and its two variants. Second, we use tvar check on the int and then on the other argument, this int arrow int type. Finally, we type check the body, and we do that in an extended environment where apple is bound to a function that takes in an int and returns a fruit. So overall, this example will be well typed, and we'll use the rule for checking a function application to know that the body is correct. Here's the start of the rule for match. First thing to do is look up that defined type, type name. We'll use a helper function for that, define type lookup. Then we'll want to do something along these lines down below. First, type check that test expression and make sure that it has defined t-type that matches the type name we're working with. Second, type check those right-hand side and left-hand side cases inside the match and do those both inside an extended environment. For example, if we're matching on the variant apple 10 at the fruit type, we need to make sure that apple is really a fruit, which it is. And then we need to type check the right-hand side 1 and right-hand side 2 in extended environments where A has a type binding and B also has a type binding. Here's the full code for that. We've added a check that the variant names inside our type definition match the tag names that we have inside match. Then we go on to type check those right-hand sides. And finally, we need to know that the two right-hand side types match up. If we try to return different types, then for now, we'll raise a type error. And that takes care of match. Now for that helper tvar check. Again, this is checking that the type we're looking at uses only names that are bound in the current type environment. Int and bool are always available. Arrow is available, but we do need to check that the two types on the inside of the arrow are also valid. And finally, for a defined type, we use this helper function again, define type lookup. As long as this lookup does not raise an error, then our defined type is valid. And that's that. The last thing to do is to implement this lookup function, but we'll skip over that. This function walks over a list, type environment, looks inside for a tdef, where the type name is a match for this ID symbol that we have here.